Welcome to the lecture series on digital electronics 18EC302C. So in today's lecture, we will introduce the circuits made by using logic circuits. And specifically, these circuits are called combinational logic circuits. So we'll look at what is meant by a combinational logic circuit in this lecture, and we'll also introduce the first combinational logic circuit and how to design the combinational logic circuit. And what is the importance of the combinational logic circuit practically. So these are the things that we are going to discuss in today's lecture. So before going to see the combinational logic circuits, so we'll look at what is meant by a combination logic circuit. So we'll define a combinational logic circuit. So you can see that in a general digital system consists of two types of circuits, two different types of circuits, namely a combinational circuit and another type of circuit is called sequential circuit. So then what is a combinational circuit and how it is different from a sequential circuit? So basically a combination circuit consists of logic gates where doesn't consist any memory, but it consists only logic gates where the output of the combination logic circuit, so the output of the combination logic circuit, for example at a particular instant, depends or determined only by the combination of inputs that are present at that instant. That means here the outputs of combination circuits are not affected by the previous inputs of the combination logic circuits or the previous outputs of the combination logic circuit. That means the outputs at any time are dependent only on the inputs at that time only. That means there is no dependence of the present outputs on the previous outputs or the previous inputs. So such type of circuit in general is called as a combinational logic circuit. So now what I can say about combinational logic circuit is it consists only logic gates and certain input variables and certain output variables, certain number of output variables. So here I have shown the block diagram of combinational logic circuit. So where this block, I can say that it can consist circuit. This combinational logic circuit inside it contains logic gates connected in some way, and it has n number of input variables and m number of output variables. You can see that these n input variables are processed by the logic gates that are connected and given out as m output variables. And you can see that for n number of input variables that you give to a combination circuit, there is a possibility of 2 power n number of input combinations. That means if you apply n number of input variables, we can see this, all these variables are binary variables. All these variables are binary variables. That means each variable value, the variable may take either 0 or 1 at any instant. So if you apply n such input variables to a combinational logic circuit, so there exist 2 power n possible combinations of the inputs. So the possible combinations of inputs will be, the combinations of the input variables will be 2 power n. So for example, if there are two input variables, there will be 4 possible combinations of the inputs, and if there are 3 variables, there will be 8 possible combinations of the binary input states. So for each combination, there is only one and only one possible output combination. That means, since the output depends only on the inputs at that instant, for each possible combination, there exists only one unique output combination for all those m output variables. So I can say that a combinational logic circuit is described by these m described by Boolean functions for all these m variables. Since there are m number of output variables, so each output variable is described by one Boolean function. So this general combinational logic circuit, now it is described by m number of Boolean functions, each for one output variable, and each Boolean function is expressed in terms of n input variables. So this is what is mean by a combinational logic circuit, and you may want to know what is meant by a sequential circuit. So just we'll go with the definition of the sequential circuit, and we'll make you know how it is different from a combinational circuit, because later we'll discuss the sequential circuits in detail. So a sequential circuit is the one where outputs at any instant are not only determined by the present combination of inputs, but also determined by the previous inputs and the previous states of output. So for sequential circuits, the output at any instant depends not only on the inputs at that instant, but also on the previous inputs of the sequential circuit and previous outputs also. So that means, so to have to store that previous inputs are previous outputs, we can say that the sequential circuit consists not only logic gates, but it should also contain memory elements. So this is what the difference between this combinational and sequential circuits. So we'll look at the sequential circuits later, but we define the combinational circuits here, and we are going to look at some of or we are going to design some of the combinational circuits in today's lecture. So this is the general block diagram, and here you can see that n input variables and m output variables, where a Boolean function can be written, or each output variable is described by a Boolean function in terms of n number of input variables. And for each input combinations, so there are n input variables, there will be 2 power n possible combinations of inputs, and for each combination there is only one possible output combination. So next we look at what is the general design procedure. You can see that how what a combination logic circuit consists. It consists only the logic gates, simply the logic gates, either they are the basic gates or advanced gates. Simply they consist only logic gates. So then how to design a combination logic? So these combination logic circuits are needed to design to perform various digital logic functions. So there can be a number of functions that are need to be implemented by using logic gates. For example, digital logic functions like you want to add, you want to subtract, or you want to shift the bits, etc. So to perform all these functions by using a digital system, you require a digital function, you require a digital circuit that implements all these functions. So some of the functions are implemented by using combination logic. Some other function will be implemented by using the sequential logic. Here we look at the functions and designing the circuit for those functions which uses only the combination logic. So here we outline the general procedure are the steps to follow to design any combinational circuit. So what are the steps? Here we have listed. You see that the first one is the problem is stated. So that means you need to identify or state the problem. That is, what is the intention of designing the logic circuit, or what is the actual function that you want to perform by using that combination logic circuit. So that is a problem that is to be stated clearly first. And after stating the problem, then you need to identify the number of input variables for the combination logic circuit and the number of or the output functions. And after identifying how many inputs that you give to the logic circuit and how many outputs that the function require and the combination logic circuit require, you need to name the input and output variables, or you need to assign letters symbols to the input and output variables so that those letters and symbols, because every output function uh, can be described by using Boolean function of consisting of input variables. So in order to express the function as Boolean function, you need to assign letter symbols to both input and output variables. And after assigning letter symbols for both inputs and output variables, We need to prepare a truth table. We need to prepare a truth table that completely defines the relation between both input and output variables. So the truth table must show all possible combinations of the input variables, and for each combination of input variables it has to show the output functions. The output functions may be 1, 2 or 3 also. So any number, so it has to show the input variables, and for all combinations of input variables it has to show the output functions. So this truth table now completely defines the functionality of the combinational logic that we are going to design. So now from the truth table, for each of the functions that are specified in the truth table, obtain a simplified Boolean expression. So we already said that for a combinational logic, the output function can be expressed as a Boolean expression consisting of the input variables. So express each function in the form of a Boolean expression of input variables and simplify it by using any of the method that we have learned. Either it is algebraic method by applying theorems and laws, or use the Karnoff map method. So by using any of these methods, simplify the Boolean expression obtained from the truth table. As simplification of the Boolean expression gives us the circuit which requires less number of gates, logic gates. So next, after obtaining the simplified Boolean expression, realize the Boolean expression by drawing a logic diagram consisting of using logic gates. So for every output function, you will get one Boolean expression, and for every Boolean expression, you will get one logic diagram, and realize that logic, realize that Boolean function using the logic diagram by using the various logic gates that we discussed previously. So next we'll look at the first combinational logic that we are going to design. So it is the circuit called half adder. And you can see that addition is the basic operation and the basic function performed by a digital system. And the simple addition, see, the digital systems are always operate on the binary digits or the bits, that is 0 and 1. So this circuit, that the addition circuit that we want to implement, should perform any of addition of these two bits. So the simple addition consists of four possible operations. You can see, since there are only two bits to add, only 2 bits are existing for binary. Either you add 0 to 0, or you add 0 with 1, or you add 1 with 0, or you add 1 with 1. So when you add 0 with 0, the result is 0, and when you add 0 with 1, the result is 1. When you add 1 with 0, the result is 1, and when you add 1 with 1, the result is 1 0. So it's not 10, it's a 1 0, as it is a binary number. And you can see that the first three additions produce a sum of only one digit. 0 here, 1 here, and 1 here. But you can see that the fourth operation is producing a sum consisting of two digits, that is 1 and 0. And when it produces the sum of the result of two digits, this least significant bit is called sum. You can see that this least significant bit is called sum, and the higher significant bit of the result is called the carry. So this is called carry, and this is called the sum. So when two bits are added, the result contains only one bit. That bit is treated as sum. If the result contains two bits, the least significant bit is called sum, and the higher significant bit is called the carry. And we can see that, so these additions we did manually, and if a combinational circuit performs the addition of two bits as we did, then that combinational circuit is called as a half adder. That combination circuit is called not simply as adder, but it is called as half adder. It's called as half adder. So now we want to design a combinational logic circuit which adds two bits and produces the result, that produces sum and carry bits. So now we are proceeding to design a combinational logic circuit which performs this function. So we will follow the general design procedure that we discussed, and will apply this procedure to the design of the first combinational logic circuit, half adder. So here you can see that The first step in designing is the design procedure is the problem is to be stated. So the problem here is that we require a combinational logic circuit that should perform the addition of two bits and produce a result where the result contains two bits. One is called sum bit, another is called carry bit. So here I mentioned a subscript 1. So this refers to the first step, the problem statement. So that is the problem that we specified for that design. So next one is to identify the input variables and output functions. So that means we need to identify the number of input variables and the number of output functions for the half adder circuit. So since we want to add two bits, we identify that the half adder has two inputs, and since we say that the result contains carry and sum, we say that the half adder has two output functions, or I say it has two outputs. So this is identifying the input variables and output functions, the second step. So we indicated that a half adder has two inputs and two outputs. So this is the second step. So the third step is the input and output variables are assigned letter symbols. So we already said in the step 2 that the half adder has two inputs and two outputs. So now we give letter symbols to those two inputs and two outputs. So let the input variables, the first bit and the second bit called agent and addend that are to be added, be designated as A and B. So we have assigned the letter symbol A and B to the two inputs that are to be added, and the output functions designated by the letters S for sum and C for carry. So this completes our step 3 in the design procedure. So next we'll look at what is the next step. The truth table is to be prepared, which completely defines the relationship between the input variables and output functions of the circuit. Now we can see that we have prepared a truth table here, and in the truth table always on the right hand side will show output variables or output functions, and since we have given letter symbols, we use letter symbols for the output variables. Here there are two output variables, S and C. So S represents sum and C represents carry. And on the left hand side we always show the input variables, and since here there are two inputs, and since we have given the letter symbols for the two inputs, and here we are showing them as A and B, and since there are two inputs, so there is a possibility of four input combinations for these two variables. So we will list out all those four possible input combinations for the two variables. That means A can either, when A assumes when the value of A is 0, B can be either 0 or 1. And when A is 1, B can be either 0 or 1. So in this way we'll get 4 combinations. Or I can also say these combinations as both A and B are low, one combination, both A and B are high or 1, another combination, and A is 0, B is 1, one combination, A is 1, B is 0, another combination. So we'll get 4 such combinations because there are 2 variables. If there are 3 variables, we will get 8 combinations, and if there are n variables, we will get 2 power n input combinations. And for each combination, you have to show what is the output function. So when the two inputs are 0, that means you are adding 0 plus 0, the sum is 0 and the carry is also 0. And when you are adding 0 with 1, the sum is 1, there will not be any carry, so carry is 0. When we are adding 1 with 0, the sum is equal to 1 and there will not be any carry, so carry is 0. And when we are adding 1 with 1, we have already seen 1 with 1 results in 1 0, where the sum is 0 and the carry is 1. So this is the truth table which defines the function. You can see that the step 4, to prepare the truth table which completely defines the relationship between the input variables and output functions. So these two AB are the input variables and SC are the output functions. Now we prepared the truth table for all combinations of inputs and we have shown the output functions for each combination of the input. And what is the next step in the design procedure is to simplify or obtain the Boolean expression for each of those functions or express each function, each output function as a Boolean expression and simplify it by using any of the method that you know. So here you can see that when you observe the sum function, so since it is a very small function and you can see there is some similarity of this function to the already learned function, so we will not be using actual algebraic methods or Karnoff's map method for this very simple function. So we'll be using that whenever it is required. So here when we see the sum function, you can see that this sum function is similar to the XOR function that we already learned. You can see the truth table is very similar. The function is 0 when both the inputs are same, either 0 0 or 1 1. The function is 1 when both inputs are different. You see that the sum function is very similar to is exactly the same XOR function. So for XOR, we know the Boolean expression is A bar B plus AB bar. And similarly, you can see that the carry function, if you look at, the carry function is true only when both inputs are 1. And if you see that this carry function is exactly the AND function. So here, see, this will not happen for all the output functions. So here it is exactly the same as the previously learned function. So instead of using algebraic methods and instead of using keymaps and etc., we'll be directly comparing that with any of the already learned functions. And since here the functions are same as the already learned function, we are directly writing. So for the coming circuits will, if you could not write it directly, we will see the procedure of how to write and simplify using the other methods like kernel method. So here you can see that the sum function is exactly same as the XOR function, and carry function is exactly same as the AND function of the input variables. So we'll directly write the Boolean expressions. So this is the fifth step in the general design procedure. So sum function, the Boolean expression for the sum function will be a bar b plus ab bar, which is same as the XOR expression, XOR function, and the carry output function. The Boolean expression is same as the AND function of the input variables, which is a dot b or simply ab. And you can see that, so we have obtained the simplified Boolean expressions for both the output functions. And you can see that the final step is to realize the Boolean expressions by drawing a logic diagram using logic gates. So this is a direct for sum. In order to realize the sum function, see that this is the sum function is exactly XOR function. So if you give A and B as inputs for an XOR gate, the output of the XOR gate directly realizes the sum function. So the sum function here is realized by an XOR gate whose inputs are A and B. Similarly, I can realize the carry function. Since the carry function is same as the AND function, the carry function is realized by an AND gate when the inputs are A and B. So this is a simple circuit. So here both XOR gate and AND gate will show the same inputs because these two are the inputs for the combination logic circuits. So this sum function is a bar b plus ab bar, which is the sum output function, and this carry output function is a b, which is similar to AND function. And this is the logic diagram and the combinational logic circuit called half adder circuit. So just we'll review what we have learned in this class. So we define what is meant by combinational logic circuit, and we differentiated it from the other type of circuit called sequential circuit. Next we have outlined a general design procedure, the various steps involved in the design of the combinational logic circuit, and we introduced the first combinational logic circuit, which performs a simple addition of 2 bits, and the design procedure is carried out as per the general design procedure that we outlined in the lecture. And finally, we are able to design our first combinational logic circuit, which performs a simple addition on 2 bits and produces the sum and carry outputs. So going further, we'll design more combinational circuits that are used in a variety of digital systems and provide important or realize important logic functions. Thank you. As we have obtained our first combination logic circuit, let's look at whether this gives the same functionality or not. By applying in the various combinations of input, we'll check whether the sum and carry output functions are implemented correctly or not. So here you see that when I apply 1, when I apply 0 for A and 0 for the B input, so that means when I want to add 0 with 0, and you can see that the inputs for this XOR gate are 0 and 0, 0 and 0. So both the inputs are 0 0 for this XOR gate, and it produces when for an XOR gate, when both the inputs are same, the result is the output is 0. So when I want to add 0 with 0, it is producing a sum of 0. And similarly, for this AND gate, the two inputs are zeros. And for an AND gate, when both of its inputs are zeros, the output of AND gate is 0. And you can see that when I add with 0, the combination circuit called half adder, giving me the sum output as 0 and the carry output as 0. And similarly, you can check other combinations also. We'll apply the second set of inputs or second combination of inputs, that is, I want to add 0 with 1. So in that case, A equals 0 and B equals 1. So the two inputs for this XOR gate will be, one of the input will be 0, other input will be 1. So for this XOR gate, the inputs are 0 and 1. We know that the output of XOR gate is 1, since the two inputs are different. Similarly, these two are also the inputs of the AND gate, and when 0 and 1 are the inputs of AND gate, we know that from AND gate functionality, the output of AND gate is 0. So that means now my circuit, when I want to add 0 with 1, 0 with 1, it is giving me the sum of 1 and the carry of 0. Next, I look at the third combinations of bits that I want to add. So the third combination of the inputs that I want to add are, I want to add 1 with 0. So these two are the inputs that these two are the bits that I apply as inputs for this half adder circuit. So and these two are also the inputs of the XOR gate, and when 1 and 0 are the inputs, the output of XOR gate is 1, as the two inputs are different, and these are also the bits which are inputs for the AND gate, and when 1 and 0 are the inputs, the output of AND gate is 0. And here you can see that the half adder combination logic circuit, when that is adding 1 with 0 to produce a sum of 1 and a carry of 0. So this is also okay. Next we will look at the last combination of addition, that is I want to add 1 with 1. So these two bits are applied as inputs, and these two are bits are the inputs for XOR gate also, and the output of XOR gate will be 0, as the two bits are same, identical. And these two are also the inputs for AND gate, and when both inputs are at 1 for the AND gate, the output of AND gate is 1. And you can see that here the circuit adds 1 with 1 and produces 1 0. The result is 1 0, where 1 is the carry and 0 is the sum. And you can see that from the previous truth table, we verified that our first combination logic circuit performs the addition of two bits perfectly correct. Thank you.